Hey folks, in this video I'll tell you about implicitly defined functions and how we can take their derivatives and what that means. So to start off, let's look at an example or two examples where we need to use some of our derivative shortcuts. These look a little weird based on the ones that we've previously done because, well, if you see, the functions f and g show up right in the middle of a function expression. So for example, on the left, I would like to know the derivative with respect to x, d dx, of this function that is x squared times f of x, where f is some function. Now, we don't know what f of x is, so our answer will involve f and probably f prime. But what we can recognize here is that two things are being multiplied, x squared, which is a function of x, f of x, which is clearly a function of x. So in that case, we need to use the product rule. So let's write this down carefully, apply the product rule. We've got our first factor, x squared, times the derivative of the second factor. Really the best we can say is that's f prime, plus, per the product rule, the derivative of the first factor, well, the power rule tells us that's 2x, times the second factor, f of x. And we're done. We really can't say anything better about the derivative of this expression. So, in other words, the way that this changes, the rate of change in this expression as x changes, depends on the value of f and the value of f prime. Let's look at the second one. This one has a little more going on. We want the derivative of the square root of this function g of x minus f of x squared. Well, we've got a square root over the whole thing, and if we think of that as an outside function, then everything inside the square root is an inside function, and hopefully we realize that this is an application for the chain rule. In fact, let me rewrite that square root as a 1/2 power, so it's clear how we can apply the power rule. And now applying the power rule carefully, well, that part is hopefully easy, but the chain rule tells us then we need to multiply by the derivative of the inside of that expression. So here I'll just write it in terms of that expression, reminding us we still need to take the derivative. So I can rewrite that minus 1/2 power as a square root in the denominator, but let's carefully take this expression from the inside and take its derivative. We get, well, the derivative of g is g prime, and the derivative of f of x squared, we need the power rule because we've got something squared, so the 2 comes down, but we also need to multiply by the derivative of f. This is again an application of the chain rule. We've got an inside function, that's f of x, an outside function, that's this power of 2, and so the 2 comes down, and then we multiply by the derivative of the inside, f prime of x. So here we use the power rule and the chain rule. So that's a beast, but that's what we get by carefully applying all these ideas. Now let's look at a slightly different but very closely related example. Suppose we have a relationship between x and y that's written this way, y squared equals x. I want to know, in this relationship, what is dy dx? And what does that question even mean? So let's start there. When we say dy dx, we mean the derivative of y with respect to x. That is, assuming that y depends on x, or that y is a function of x, how does the output, the y value, change as the input, the x value, changes? So to do this, maybe let's make that a little more clear. Instead of writing y, let's write f of x, because y we're treating as a function of x. And if I do that, we get f of x squared equals x. And hopefully now you see why this is related to the last example. Now, if we want to talk about dy dx, a derivative, we need to differentiate. Well, we've got two sides of an equation, we can't just differentiate one or the other. To keep things equal, we'll differentiate both sides. That is, we'll take the derivative with respect to both sides of this equation with respect to x. And now the right side is easy. The derivative of x is just 1. That's an application of the power rule. And the derivative of the left side, well, we saw this in the previous example, but let's revisit it. We've got a function f, and that is squared. It's raised to the second power. So the inside function is something called f of x. The outside function is the square, or this power. So using the power rule, we bring the 2 down to the front. We drop the power to 1. We don't need to write that. But then we multiply by the derivative of the inside function. The best we can say is the derivative of f is f prime, and we get this. But now remember, we introduced f into this situation. F was really just standing in for y, sort of like a stunt double. So now that we're done all the calculus, all the differentiation, let's let the original actor or actress come back in. We'll replace f with y. F prime, well, that's the derivative of f, or the derivative of y. We can write y prime, or we can write dy dx. And that last expression we can write this way: 2 times y times dy dx, or y prime if you prefer, equals 1. The original question asked, what is dy dx? So, well, let's solve for that quantity. We can we can divide both sides by 2 and divide both sides by y, and we get dy dx is equal to 1 over 2y. So that tells us that the derivative, the rate of change, how y changes with respect to x, depends on the y value at a point. And I'll make a sidebar observation here. This original function, y squared equals x, we can solve that for y. Actually, we didn't do that here, but we could have, to find that y is equal to the square root of x, at least for proper values of x. And of course, we know the derivative of that function. Hopefully we know it. But what we've just done is recovered that derivative shortcut in a different way. That is, if we replace the y in our dy dx expression with square root of x, we get dy dx is 1 over 2 times the square root of x. That's the derivative rule for y equals the square root of x. It's time for some definitions. On this page, I'll define for you the difference between an explicitly defined function and an implicitly defined function. The first is basically what you're used to when you think of an equation, y equals something. That is, an explicitly defined function is given in the form y equals some function of x. That is, we can write on one side y equals, and we can write on the other side a function that depends only on x and not on y. So here's an example of an explicitly defined function. You put in an x value, you can compute this thing on the right-hand side, and then you get the y value on the left-hand side. On the other hand, an implicitly defined function is one where, well, maybe it's not as clear-cut, but we get just a relationship between x and y. We get some equation, possibly with x's and y's on both sides, and, well, if you want a solution, you can't change one without the other, but it's not clear how that rate of change behaves. So when I say a relationship between x and y, I mean something like, well, the example we just saw, y squared equals x. It's clear that x and y have a dependence on each other, but it's not as easy to find a value of y if I give you a value of x. Another example, x squared plus y squared equals 1. So I'm sure you could find some points x, y that make this true, but again, it's not as easy as just plugging in an x value and seeing what y equals. So if you've got something, an equation where you can't easily solve for y and have only things depending on x on the right-hand side, then you've probably got an implicitly defined function. In the next video, we'll talk about how to do implicit differentiation, and we'll work through some pretty fun examples. Well, I think they're fun.